This video is a continuation on the 1.6 transformations of parent functions. We're going to be focusing now on two more transformations, stretches and shrinks. When you walk away from this video, there are two objectives that you need to pay attention to. You need to be comfortable with recognizing what multiplication does in the equations of these parent functions. What does the multiplication do to the graph? The other thing you need to be aware of is whenever given a graph, you need to be able to come up with the equation by just looking at that image. You don't have to write these down. These are just review of the transformations that we already discussed in the previous video. At this point in time, whenever you see addition or subtraction, you should be thinking to yourself, oh yeah, addition or subtraction moves my graph, either up or down, left or right. So addition and subtraction shift. If ever you see negation symbols, or a negative x, or just negation, what you're going to be saying is, I know that this is going to be a flip. So a more mathematical term of that is actually a reflection. Now when you see multiplication, this is the new one, if you ever see a multiplier somewhere in your function, that's what we call a scalar multiple. So it's just a multiplier, a number multiplier, also known as factors. But you see this constant number multiplied on, what you should now be thinking is, oh, that's a stretch or a shrink. So here, if you look at this notation, all it's saying is that we have a number multiplied onto the x, where a is just a number. So for a more concrete observation, let's say f of x, we're going to study our parent function, the cubic function. If I wanted to multiply something to the x, oops, I'm going to have to call it something else. It looks something like this. So now you would be seeing, okay, I see the multiplication here. I'm thinking stretch or shrink. And I see that it's directly attached to the x. It's horizontal. Now I have to determine what exactly that does. I don't necessarily expect you to memorize that if your scalar multiple is less than 1, then it's a horizontal stretch. What I want you to do is think about it in terms of what we've been learning with patterns, that whatever is attached to the x does the opposite of what we would think. So you're looking at this and saying, alright, it's 1/3 the width, or the horizontalness of this. And being that it's 1/3 of it, and you're thinking it's going to be skinnier, it actually becomes wider. So think about it horizontally, and I'm stretching it out horizontally. So this is, in other words, becoming wider. Okay? So take a moment to kind of think about that. Versus, if I were to look at h of x, and then I'm going to take 3x to the third, you can look at it mathematically and say, alright, the absolute value of this thing being multiplied onto the x is greater than 1, and it's a horizontal shrink. Think about it in terms like this. You would think that being 3 times the x values, or 3 times the width, it'd be getting wider, but it's the opposite of what we think, just as everything is when it's directly attached to the x. It's going to become skinnier. So it's a horizontal shrink, or in other words, I'm going to say skinnier. Alright, so there are those. Now let's look at it. What if it wasn't directly attached to the x? So we're again going to look at x cubed, and I'm going to call this k of x equals, so this is a little deceiving. I'm going to do 1/3 x cubed, and you're going to say, but isn't that directly attached to the x? No, it's not, because it's not being cubed with the x. It's on the outside of that cubic function. So this, you're thinking now, alright, not directly attached to the x, that's vertical, and it's multiplication, so it's stretch or shrink. Alright? So again, I don't expect you to memorize this necessarily, but what I want you to think about it in terms is this. We're looking at it vertically, and so we're thinking, alright, we're either going to stretch it, or we're going to make it flattened, or we're going to shrink it, so squish it down. It's 1/3 the vertical height. So 1/3 of, let's look at Stretch Armstrong. If I were to squish him down to be 1/3 the height, he's going to squish out, right? Because he has to fill that space somewhere. So this is what we call a vertical shrink, because we're shrinking it down. It's going to, again, make it wider. Alright, again, we're saying it's not being cubed with the x, so it's vertical. And you'd be saying, oh, it's 3 times the vertical height, so it's going to be stretching that Stretch Armstrong out. This thing is going to be a vertical stretch, exactly what you would think. it's going to become skinnier. Okay, so I went ahead and graphed these. There's a couple of ways you can do this. You can just go directly with the graph and apply the transformations, or you can make a chart. So I'm going to do both for you. For this one, let's go ahead. We've already applied the idea of adding 1. This is going to be a shift up. So we're just building on to the other transformations that we have studied. So we think squiggly when we think x cubed, right? And then we're going to say, all right, we're going to bring it up 1. So here's my new origin, that key point that we always work off of when we're graphing our parent functions. And we would be going over 1, up 1, over 2, up 8, just like we would do if we had been sitting on the origin. So that blue line is graphed. All right, now let's look at this red, which I graphed on line. So 2x cubed plus 1. Again, we have a shift up. All right, when we're directly going off the graphs, we always apply the shifts first. So we shift up 1. Now we're looking at this and saying, all right, we had the addition, knew what to do with that. The multiplication is our new one. That's going to be our scalar multiple that's going to either stretch or shrink it. So being that it's not directly attached to the x, I know it's vertical, so it has to do with the y values, just like this had to do with the y's. Right? And we're going to say this does exactly what we would think. It's a vertical stretch, being that it's 2 times the size, so it's 2 times those y's. So now if you went to the graph, we did our shift up, okay, because we always do our shifts when we're doing our graphs. Then we're going to apply the other transformations. So instead of going over 1, up 1 to get that blue line that I had over here with no stretch or shrink, I'm going to go over 1 and then up 1, 2. Okay, to get one of my points on my new transformed graph. Same thing, if I went back 1, down 1, I get that blue, but I'm not doing that. I'm going back 1, down 1, 2. Okay, so that's where you would get those points for the red lines. If you went over 2, over 2, we would normally be going up 8, but instead we're going to go up 16 to be way up here. Alright, so there's the red one. And then now the blue one, we're going to do it directly off the graph again. So we know this is up 1, so that's going to affect the y's. And this one is the opposite of what we would think. We're actually going to do 1/2. We're going to divide by 2 all the x values. So in other words, 1/2 to the x values. This is our horizontal. And what we would say then is it's a horizontal, not stretch, but shrink. It's the opposite. Okay, so we did our shift up 1, okay, and then now we're going to say 1/2 the x values. So instead of going over 1, up 1, we're going to go over 1/2 up 1 for that green point. Instead of going over 2 and then up 8 to be up at this 9, we're going to go over 1 up to 8. Okay, and you can see that x value is half the size. Okay, so we're seeing how you can do it straight off, just knowing what that parent function looks like and modifying those points of how far over and how far up you go. The other way we can do this is I'm just going to do the chart method for this one for now. So we're going to look at y equals just x cubed. No transformations, no nothing done to it. It's stripped down. Okay, so now we're going to apply these where they belong. We need to make adjustments to the y's, and it would be in the order of operations. So we're going to have to multiply these y values by 2. So I'm going to multiply this by 2, multiply it by 2, multiply it by 2, 2, 2. And then we're going to add 1 to it. So negative 8 times 2, this is going to get our new g of x function. G of x. So we again had the same, nothing happened with the x values because there's no horizontal transformations, but we have to calculate these, so this is going to be negative 15. This 1 times 2, and then plus 1 is going to get us 3. 8 times 2 plus 1 is going to get us 17. So now if we were to graph these, we would go back 2, and then down 15, which I'm not going to do, but I'm going to go back 1 and then down 1. There that is. I'm going to go 0, up 1. I'm going to go 1, up 3. There that is. And then over 2, and then up 17. So I'm not going to do that one. But there you have it. Okay, so I have x cubed plus 1, there's my blue line again. And this time I'm going to mark, again, up 1. So the y values are all plus 1. Alright, here we're going to be, again, having the y values times 1/2. So that's going to be doing exactly what we would think. It's a vertical shrink, because we're one-halving all of our vertical values, our y values. So you could do this visually, go our up 1, and instead of going up 1, or over 1, up 1 for my blue line, we're going to go over 1, up 1/2 for getting this red line. Okay, and then same thing with the same thing with the backwards motion. So there you have that. I'm going to focus more on this one now. Alright, so we have our up 1, so plus 1 to the y's. And now this is directly attached to the x, so we know it's horizontal. And then you would think that it's going to do 1/2 times the x's, but it's going to be, in fact, all the x values divided by 1/2, so it's times 2. So it's a horizontal stretch, opposite of what you would think, and we're going to apply that now. So here we shifted our parent function up, our squiggly up, and now instead of going over 1, up 1, we're going to go over 1, 2, and then up 1. Okay, instead of going over 2, up 8, we're going to go over 4, over 4, up to 8, which would be up here. Okay, same thing with the backwards motion. Now I'm going to do the chart for this one. So we're going to again graph y equals and then x cubed without anything on it. Alright, so now we're going to apply all the transformations in the proper order of operations. The very first one that we would do is we would take 1/2 times x. But again, it's the opposite, so we're not going to take 1/2 times x, we're actually going to take it times 2. So all these values have to be multiplied by 2. So I'm going to just write that over there, -2, 0, 2, 4. Over here, we're going to add exactly what we think. It's not the opposite. We're going to add 1 to all the y's, so we would get -7, 0, 1, 2, 9. And if you graph these, we would go back 4, down 7, okay, back 2, 0, 0, 1, over 2, up 2, over 4, up 9. Okay, so either way you do it, chart or graph, it's up to you. We hit objective number 1 in being able to look at an equation and being able to graph, or just looking at an equation and being able to know exactly what's going on with the graph given all the transformations. Now we have to go the other direction. So given a graph, could you come up with the equation? The biggest thing is, I think at this point we know how to do the transformations of shifts and flips and apply that to an equation, but would we know how to solve for the scalar multiple? And that's a little bit harder to do, so it involves some algebra technique. So basically what you're going to be doing is you're going to be coming up with the equation and plugging in the transformations and recognizing that you're going to have to solve for our scalar multiple, or for our a. So we'll use an xy solution point to do that. So what you'll do is you'll just recognize what parent function is involved, okay, and then you'll start tagging on all of the different transformations involved. So this one, it's easy enough to see that, hey, I went down from the typical origin point, and I went down 3. So I'm not going to directly attach it to the x, it's going to be on the outside of the absolute value bars to keep it away from the x. And then the harder thing to identify, what I would just always, as a safeguard, do is I would put a multiplier on as a vertical stretch or shrink. So you could put the a in with the x, but you might as well, it's easier, I'm just going to tell you, it's easier to do it not with the x. Either way, if you had put it with the x, you would be able to solve it and it would just be fine to do, but it's easier not to do the horizontal method. So just tag on a multiplier, and now we're going to have to solve for it. So we've nailed all the transformations. I know that there is a shift down. I'm not really sure if there's a stretch or shrink because it's harder to visually see. I'm going to say that yes, there is, because typically the parent function of the absolute value would go back 1, up 1, back 2, up 2, right? And so you can see that this is a lot skinnier than what it should be. So I know for sure I have that A. So what you'll do in the last section of your homework or of your practice problems, they're going to give you a point. And it will be something you should always check to do, but I'm just going to say the last chunk of your homework problem you have to solve for an A. So when you do this, we need to find out for what value of A would have made it so that this is a solution point. So what value of A would have made this a true statement if 3 and -2 had been plugged in? So I'm going to plug in those values for my x and my y, and I'm going to solve them for what value of A would have to hold true to maintain this. So simplify where you can, and then just use the reverse order of operations. So here we have A is equal to 3. So this is always the method. You'll know the transformations that you have, and then you'll slap in an A and solve for it. So you need to solve for the scalar multiple. So at the very end, we're not really quite done because we wanted to come up with an equation for this graph. Just go ahead and go back and plug in the A that you found. Okay, and to be even more precise, label it a function because we know it is, and now everyone else does too. Okay, there are your problems.